Welcome to everyone joining us this afternoon. I'm Crispian Lees. I'm the head of education at Advantage Learn. And essentially, it's about an opportunity for maths educators to connect with thought leaders in the high school maths space. And then also to find out a little bit more about our Neo Series resource for high schools in maths. We're going to kick off with our keynote address from Craig Pournara.
Good afternoon, everybody. Thanks again for the opportunity. This whole thing of senior phase geometry has become something that I have become particularly interested in, along with my colleagues in our project, because it's kind of a space where, in a sense, many people have just chosen not to go. The problems in senior phase across the country are so massive, even if they're not as huge maybe in some of the schools where you teach, that in a sense, we've just kind of skipped geometry and focused on algebra. And in our project, we've done that, at least for 10 years. But as we've got more into the geometry space, we've realized that there's a lot to learn, that we've had to learn. And I really hope that what I've got to share this afternoon is going to be useful, because that for me is what these kinds of sessions are about. So when I talk about it being a new game, it's not that I've got something, it's not that there is a new game that's emerging. It's really about the game changes in the senior phase. And because the game changes, it's hard for learners and therefore it's hard for teachers. And so I want to share some of those things today and some thoughts on how to grapple with it. 25 minutes is going to go hangover fast. I'm going to talk fast because that's just how I am, but I hope that it's going to make sense. So here goes. What to expect, there's a whole list of things, and I'm not going to read them all out to you, but just browse them to get a sense of what's coming. I want to focus on certain issues. This is not going to be systematic, exhaustive. It's just not possible in 25 minutes. But I hope that I can at least spark your interest and give you some things to think about. I want to start by talking briefly about this idea of the geometric eye, which was introduced by a guy called Charles Godfrey in 1903. That's like over a century ago. But it's a really interesting idea, and it's kind of an image for me that I think is powerful, because it's saying that geometric eye is not just about being able to picture shapes in one's mind, but also being able to see the properties of those shapes. So those properties are kind of stuck in your mind at the same time, but of course they don't just jump into your mind, they come through experience and through exposure. And it's that kind of stuff that I want to talk about today around what opportunities do we give learners in the senior phase. And when I say senior phase, I'm really thinking particularly grades 8 and 9, and that fits with the Advantage Learn focus of secondary school. Okay, so what makes senior phase geometry difficult? Well, I think one of the things is that, at least in theory, we're moving from cutting and folding and measuring pieces of paper, pieces of cardboard to formal proof. And that is a massive jump, which I think, certainly I always underestimate. Then we're working with diagrams and text at the same time. Now we're doing that with graphs as well, but somehow the diagram text relationship in geometry is not quite the same. And so learners are needing to make links between those representations. That's a skill that we need to teach them. Then there's the spatial skills, and part of that's the geometric eye. And so specifically thinking about diagrams, there's stuff about orientation, there's stuff about complexity of the diagram. And then in the senior phase, one of the things which really comes to be an issue, I think, is what you can assume from the diagram. Because in the intermediate phase, it was like what you see is what you get. Now suddenly they keep telling you the lines are straight, or they don't tell you the lines are straight. It looks like a right angle, and then you assume it is, but actually it wasn't. And so in that diagram that's on the screen right now, it looks like a right angle, right? But you're not told it's a right angle. So can you assume it? Two of the angles are marked, and there's a number in one of those angles. Does that mean 28 degrees is the size of both those angles? It's not clear. And these are some of the things that we come to know and work with by intuition in some ways as teachers, and the successful learners do that. But the learners who struggle often are trying to decode this stuff. And my interest is always in the learners who struggle with maths and the learners who go to school in contexts where they have far fewer opportunities than maybe in your schools. And so those are the learners I'm particularly concerned with. I'm not focusing today on the top kids. I'm focusing on the kids who want to learn maths, but it's difficult. And having said all that, of course, we've got this introduction to reasoning and proof. And we don't need geometry to introduce reasoning and proof, but it's kind of the mechanism that the South African curriculum has chosen in mathematics. So there's this issue of transition to abstract aspects of mathematics and the building of logical arguments. And I don't need to tell you that that's where many learners just struggle immensely. That said, I'm also aware there's some learners, and my son is one of them, who thinks geometry is way more fun than algebra and function. And I actually think that kids with those skills grow up to benefit a lot in their adult lives. The other thing that I think we have to fight, I'm not sure fight's the right word, but I've used it, is our curriculum. Firstly, I think there's too much focus on formal proof in grades 8 and 9. And I think that is a throwback from the ANA, the Annual National Assessments, which stopped a few years ago, but we still live with some of their impact. And I think the other thing is that the curriculum doesn't provide enough time to develop geometric reasoning skills. So even if we can get through all this other stuff, the curriculum is not on our side in terms of, I think it's asking too much and not giving enough time for it at the same time. It's like a double whammy. So I want to talk now about 4 key transitions in senior phase maths. And I did this deliberately because it's not just about geometry. And maybe we chat about this a little bit more in the Q&A. But the transition that is key in senior phase maths, and these are not my ideas, they're taken from international research. But there's a transition from numeric and calculation-based mathematics to an abstract and symbolic form of mathematics, which is clearly more complex. So here are 4 instances of that. A transition from whole number to fraction to negative number and eventually to real number. Anybody teaching the beginning of grade 8 knows the struggle that you have just sorting out those moves. Then from operating on numbers to operating on algebraic symbols. And again, I don't need to tell anybody about this, but let me illustrate where some of the struggle we really think is. In the first example there on the left, you've got a single value for an answer, and that is what learners are used to. In the second example with the algebra, it looks like the answer is unfinished. There are 2 terms. There's an operation that still needs to be performed. And so typically they do it, right? And they end up with 21K. That's part of this massive transition that needs to be made in accepting that 5 plus 16K is the answer to that algebraic simplification problem. The third is a shift in going from rules which are based on counting and numerical examples to rules which are derived through logic and definitions. And I'm going to work with negative number here, but I've got to start with whole number. So 4 times 3, we can see that as 4 groups of 3, and we can draw an image of that, and everybody's happy. Then we move to 4 times negative 3. Well, maybe that's 4 groups of negative 3, and maybe you can live with that, but it's already starting to get a little wobbly. But then you get to negative 4 times negative 3, and seriously, you can't talk about that as negative 4 groups of negative 3. So in come all the rules about integers, and now for some learners, maths just becomes ridiculous because it doesn't make any sense anymore because it's not about counting. And then the change in relation to shape, from a focus on features of tangible shapes that you can cut up and fold, etc., to a focus on properties of shapes, the relationships between the properties, and then logical arguments which lead to proof. So those are 4 key moves that happen from probably starting in grade 6, but certainly all the way through to grade 9. And our research shows that there are many learners in grade 10 who are still struggling with these transitions. And you as teachers, if you're teaching in these grades, I think these are amongst your biggest challenges because they don't get sorted out in an individual lesson. It takes time to move learners through it. And of course, they don't all move through it at the same rate. So if learners don't master the foundational knowledge of the earlier grades and be able to apply it, then they have difficulty making these transitions. So if you've got learners coming in, particularly at grade 8 level, who's struggling with primary school maths, then these transitions are way more difficult. And I'm not telling you anything you don't know. So you might start with geometry ideas in primary school, top end of primary and high school, where you're looking at logos maybe, and you can start, depending on the ones you choose, to look at things related to lines and angles and triangles. So here, with the chevron and the Adidas symbol, I'm imposing a geometric gaze and a geometric eye on it. I'm deliberately looking for parallel lines. I'm seeing transversals, which are horizontal. That's not the way we normally show transversals, right? So I deliberately didn't want to shift around the Adidas symbol, but those are things we need to think about around orientation. Then you might be familiar with looking at the sum of angles in a triangle by folding, where you take a triangle and you fold it, and I don't have time to let you read this entire slide if it's not familiar, but the reference is there and you'll be able to pick it up later. And of course, you can Google this stuff too. So there's an idea of folding leading to the idea of sum of angles of a triangle adding up to 180. In a similar way, here is a set of diagrams leading to the deriving, if you want, the area of a triangle based on the area of a rectangle. And once again, this we can fold things in, we can start to see that we've halved the height, but we haven't changed the base. And we started with the triangle, now we have a rectangle. These are ideas that I think are really important and make part of that sense making that's key in developing a geometric eye. But now we need to start making the shifts. And when we do that, we see crazy things happening. So I want to share two pieces of research with you from research we've done in the last couple of years. And they're relatively large samples. So this is roughly 970 grade 8 to 9 learners, top performing government schools in Gauteng, and we collected the data last year. So the task is, what's the size of angle B? And we very deliberately gave both the angle and the length of a side. And so as an option, one of the options was then 58 centimeters. 58 degrees. And you know what's going to happen, right? So 66% choose the correct answer. And that is way higher than if we had tested a much more representative sample in the country. But there are 22% who are choosing either 8 centimeters or 58 degrees, which shows us that there are too many learners who are not yet distinguishing between angle measure and length measure. Again, I don't need to tell you this because you know it, but it just reinforces that many learners are still struggling. I'm sharing an algebra item because I want to come back to this later. So 760 grade 9 learners, 4 of the top performing government schools in Gauteng in 2018, 2 equations. One, 4x subtract 10 equals 2, and the other one, 4x subtract 10 equals 2 add x. So the only thing that's different here is that the second example's got an additional x on the right-hand side. So you wouldn't think that would make too much difference if you haven't taught grade 8s and 9s, but of course you well know that it does. So in February, 43% got the second one correct. By contrast, nearly 70% got the first one. That changes quite substantially by September, October, when we did a post-test. And notice a substantial change that happened through the grade 9 year with equations with letters on both. The reason we think that learners get the first one correct so much more easily is that they can work arithmetically and say something like 4 multiplied by x, or 4 times something, take away 10 gives me 2. Now, what could that something be? Well, clearly 3, right? Because I've got to get 12 subtract 10. But you can't use that kind of reasoning in the second one. And so suddenly now the game changes. And I don't want to go into the research, but there's substantial research that says that learners don't easily move from an equation with variables on one side to equations with variables on both sides. That is a big shift for the majority of learners, and one that's going to impact in geometry. Okay, so now onto angle. I want to push on this quite a bit because I really think that many learners are coming to high school without a concept of angle that relates to an amount of turn. And to show turn, we need 2 boundaries, and let's call them arms, and a vertex and movement. And when we use our bodies, it's relatively easy to show movement, particularly with arm movement. So I don't know what you can see of my screen, but I'm trying to use my forearm and show this idea of one arm standing still and the other one moving. And I think that idea of having the vertex at the elbow is probably something that you all do. We can do it with pins and rods and stuff like that, but we also have to represent it on paper and on screen. And I think this is where some of the challenge comes. And having spent a lot of hours in schools this year, I've looked a lot at the posters on the walls. And the images I'm going to show now are not posters on the walls of classrooms, but they come off the web. And I'm doing this to kind of provoke us to think a little bit more carefully about what it is we see when, or what learners might see when they see these images. So the top one is nice and colorful. It shows a right angle, an acute angle, an obtuse angle, and believe it or not, a bisected angle. But of course, there's no indication of turn there. And so perpendicular lines look like a cross. Intersecting lines, of course, are also perpendicular lines, but we won't go there. It's a bunch of stuff here that I really don't think communicates very much at all. The second one is lovely because the colors are so nice and bright. And you've got like a sunrise going on there, and then maybe a Pac-Man, and then a full circle with a line sticking out of it. But again, doesn't show anything about turn. And your eye goes to the space that's colored in. It doesn't go to the stuff that we want learners to pay attention to. So stick with me with a few more examples. Here, I've taken this off the web. Now, here we start to see two arms with different colors, which is useful provided you're not green, red colorblind, right? And so I think there's something a little bit more useful here. There's a sense of angle, but no indication of the direction of turn. And then there's a full angle, which apparently is 360 degrees. And I mean, the people who are designing this stuff know what they do, right? But what they're communicating is not, I don't think, what we really want learners to get and to grasp about angle. Here's another one. I'm not quite sure what's going on with those first two diagrams, but at least with the 45, 60, 90, etc., you have an indication of arrows, but I'm not sure whether arrows are indicating movement or whether they're pointing to the arms. When you get to the 180-degree thing, you've got a straight line with like a sunrise without the sun in it. It's not showing the vertex, and I think that that's really important. So take a look at this one. If you look at this one now, you've got an emphasis on vertex, an emphasis on turn, and the straight line angle, which of course is a bit of a weird phrase, but nevertheless, gives you a sense that the angle has opened, hopefully from the left across, from the right to the left. So it's turned in an anti-clockwise direction. The right angle thing, if you keep looking here, notice in most of, or you might have noticed, in many of the diagrams I've shown, the right angle is shown as a corner, right? Which is how we represent it in many parts of the world, but not everywhere. But it doesn't show turn in this case, the second image. The first one shows it as a curve, which I actually think makes more sense because then there's continuity from 60 to 90 to 120, etc. And the idea of this corner is really to specify that this is how we indicate 90 degrees. It's not showing turn. So maybe I am really milking this beyond what's useful, but I want to suggest that we need to pay more attention to this idea. I want to share with you now a task that we've used in our materials to try to push this idea of rotation and turn within a Euclidean geometry context. So PQS is 40 degrees, and QR is rotating anti-clockwise so that SQR is 110 degrees. In other words, I'm trying to get this idea that there's movement going on and that arm QR is moving in some way. So the task then for the learners is how many more degrees must it rotate so that PQR forms a straight line. And of course, the other one I've got there is so that SQR forms a straight line. And so obviously we're rotating more. But we think that this might be the kind of task that might, within a Euclidean geometry context, still get learners to think of angle as turn and not as a fixed thing with a number in the wedge between the arms. I want to talk now briefly about using variation in choosing diagrams. And this is something that was brought to our attention a lot as we started to look at textbooks, particularly at grade 8 and 9 level. So on the screen, you have 3 diagrams. They all are isosceles triangles. and they've got similarities and differences. And now what I want to do is go a little bit more systematically through each of them and talk about what's staying the same and what's changing. So there's 3 triangles. What changes across the 3 is the shape, the orientation, the letters that are used, and the indicators of equal. Now, some of those to you might be trivial, but I think the indicators of equal is something that's really important to pay attention to, as is orientation. Because a triangle ABC is the classic orientation that we always see. And when we change it to something on the right-hand side, it's much harder for learners to appreciate and to see the isosceles triangle. Now I add measurements. So take a look at the choices I've made. What's the same? Well, I put one angle in each. What changes? Different angle sizes, should I say. The position that's given is different. And that, of course, is substantial when you're talking about isosceles triangles. And then the number being given as odd or even. So in triangle MKT, I deliberately chose 125, and I put it in the unequal angle because I want learners to appreciate that you can have an angle that has a fraction. So that choice of 125 is not arbitrary at all. We then add letters, right? And this is typical of what goes on at grade 8. So what changes? Well, the letters I choose to use are different, but that might be trivial. But the complexity of the algebra required also changes by the expression I use for the letter and also for where I put the letter in the actual triangle. So this gives us 9 different triangles of something that's pretty relatively trivial in some ways. Here's another way of thinking about them. Instead of looking across at the rows, look down at the columns. Because in a sense now you have one case of each of the 3 triangles, all with slight differences. And those might inform the kind of decisions you make. But I want to argue that how you select from this matrix determines the level of difficulty of the task. And I think very often we don't think or give enough attention to what decisions we're making, particularly at the beginning when we're trying to get learners to find all the size of all the angles in an isosceles triangle, as an example. Introducing algebra comes with stuff, and I'll come back to that just now. I want to talk now about working with structure, and I use the word structure in terms of what you see visually. So you're seeing something more than an individual triangle. In the case here, you've got 3 intersecting lines which have 6 exterior angles. But there are also 3 other outside angles. And I'm deliberately using the word outside, and we can talk about that later if necessary. And those angles sum to 360, right? Because using vertically opposite angles, we can get into the inside of the triangle. And so we've got this relationship about what's going on inside and what's going on outside. Now we put the whole lot together, and of course it's getting a bit busy, but now we can start to talk about, if I focus on a green circle, well, in terms of exterior angle of a triangle, what other 2 angles am I adding to get the sum of that would be represented by the green circle? And of course, there's multiple ways of asking that. But now what I want to do is simplify that diagram. So in each of those diagrams that are now towards the side of the screen, I have reduced some of the detail in the original diagram. And now I'm going to remove those blue triangles to get the kind of image that we might give learners. And I share this because I think it is powerful in starting with this basic structure that goes where you see the intersections of all the lines. And then you start to erase, if you want, different parts to form different diagrams, but still based on the same original structure. I think that this is very helpful, especially working with grade 8s and grade 9s. So now I want to talk about building up the diagram. I'm sticking with the same diagram. So here I have added a parallel line. Well, I've added a line that is parallel to BC and indicated that. So now slowly I'm starting to build up the diagram. And now I want to kind of take away some bits. So just to reinforce what I've said, I'm kind of blacking out certain parts. So I choose to erase, or whatever you want to call it, various bits so that I can simplify the diagram. I can make it look the same as I want learners to experience, or I make it look slightly different to what they typically see in textbooks. But I think this is a powerful idea of generating our own diagrams as teachers. We easily generate our own expressions and equations, but typically we stick with the stuff in textbooks. And granted that I'm doing this with people who are writing materials, I still think it's really important for us as teachers to be very careful about the range of diagrams we give learners to work with in geometry. Okay, I promised I was coming back to the algebra and geometry. So this is an example from the Advantage Learn materials. And I said to Chris I would be doing this in 1 or 2 places. So I share this with you because what you see in the diagram very clearly is specifying that AED is a straight line. CFD is 90 degrees, calculate the size of X. Okay, classic grade 8 kind of diagram. Here's another one from a few pages later. We told they're straight lines, calculate the values of X and Y, giving reasons. Now, I haven't given the reasons, but I have set up the equations. And I do this to link back to the earlier part of the segment of my presentation. Learners are struggling to work with equations with letters on both sides. And in the Advantage Learn materials, they very explicitly talk about working with algebra in geometry. So this is not a criticism of that at all. But what I am wanting to highlight is how we make it so much more complex, particularly for weaker learners, when we bring this level of algebra into the geometry. So I want to caution about that, and maybe we can talk about that in the infinitely long 10 minutes of Q&A we're going to have. I also want to talk about maximizing the potential of a diagram, because one of the things that I think is useful, and it kind of connects to what I've just shared, is getting learners to become familiar with diagrams. So if we were face-to-face, and I long for the day when I do face-to-face PD again, I would be saying, can you design 6 different questions based on this diagram and then rank them in order of difficulty? And I want to challenge you to maybe go back to your schools and to do this with your colleagues. And here are some of the advantages that I think come out here. Firstly, we reduce the overhead for learners of having to make sense of a new diagram for every task. Secondly, we start to pay attention to what changes and what stays the same. We can also work with this idea of working forwards and backwards, which comes with the idea of converse, because we can swap what's given and what must be proved. We can also start to ask what-if questions. We can build up and break down, which I've already talked about. And the other thing which dawned on me walking down the street a few days ago is that we can use it, potentially, we could use a familiar diagram as part of assessments in a similar way to how our colleagues in languages work with scene poems. Because if we deliberately choose a diagram that learners have seen before and put that in the assessment, we give them a starting point that's familiar. At least they can get started and hopefully can know this diagram. But they're asking me something new about it. So I want to challenge us to think about that. Here are some possible questions. Okay, given that stuff, is triangle KLM isosceles? And you can ask it in those 2 different ways. I'm racing now because I know I'm against the clock. Explain why LO equals NN. And I deliberately put that in here because these are the kinds of things that start to come up in grade 10, and of course more and more in 11 and 12. But what if the KNO triangle is not isosceles, but KN and NL are the same, and KO and OM are the same, but different, right? What could you do then? Then this working with overlapping triangles. I think it's incredibly difficult because spatially it's really hard to imagine. So here I'm showing the classic example of stuff, the classic tasks that we give learners. And I want to suggest that one of the key things we've got to do here is to get them to redraw the diagrams and to pull them apart. Because the skill of learning to see overlapping stuff, I think takes a long time. And if learners can't imagine that, there's no ways they can answer those revolting similar triangle questions, which they get in grade 12 or maybe grade 11. Here's another example. on the same diagram, and it's about producing the diagram from verbal descriptions. So draw the first thing, extend, and then join. And then ask learners to label the diagram, to show the equal sides, and then to move on. Okay, so working with areas of triangles, using the formula or using congruence, I think there's more possibilities with this diagram. So I really think that this is a particular diagram that's worth investing in. And then, of course, we need to rotate it 90 degrees so that that's not in standard orientation. Chris, I'm going to stop here and let's take the questions, and then I can just talk through the next bit.
Will we get the PowerPoint from Craig?
Absolutely. That's why I do what I do.
What is your take on D-Tech versus tech in studying geometry in class?
In very resourced contexts where many of you teach, kids have their own laptop, they have tech at home, they have tech at school, and that makes massive opportunities. On the other extreme, we have learners who don't even have a protractor because they can't afford to buy one. So trying to answer across that range. Where tech is possible, I think it should be used to demonstrate stuff, and the drag feature in something like GeoGebra, which I think is an amazing product, I think is incredibly powerful. What I wouldn't do in GeoGebra is get students to construct stuff in GeoGebra, because you can't draw, and I'm distinguishing between draw and construct. If you draw in GeoGebra a square and you pull it, it is no longer a square. If you construct it, and it's not trivial to do that, and you pull it, it stays a square, and you rotate it, and it's not a diamond, it's still a square, right? So I think that the skill to learn to construct in GeoGebra is massive, and I'm not sure that many teachers have time to teach their learners those, and the geometric understanding required is massive, and I think it's completely underestimated. But there are amazing apps out there for GeoGebra where you can demonstrate, and I think, and this is how we've done it, is giving teachers, pre-service teachers, in-service teachers, given the diagram and then to now pull the thing, pull on this vertex and drag it and see what changes and what stays the same. I think that is very powerful, but take away all the overhead of designing. But now let's de-tech it. So that's my take on GeoGebra. In terms of cutting and folding, I think that for many, that is the most profound experience. To recognize that when you try to fold a parallelogram along a diagonal and the corners don't join up, I think is quite an aha moment, because kids then try the other side, they fiddle and they rotate it and whatever. Just recognizing that they don't line up is something really important. You get that by folding. You get it by cutting to some extent. I definitely recommend that. But I think our key thing in the senior phase is the transition that's got to be made. So we've got to make the link between what we were doing with paper and drawing and folding to what this diagram now is. And I think what might be a way to push that is to always get them to draw a drawing of what they've been doing with the folding. So it's a long answer, but I think this is a tough and a worthwhile question. I have to say that if I could change the intermediate phase geometry curriculum and make it more substantial, I would do it, because I don't think that we're doing justice to this geometry stuff in the intermediate phase. But I didn't want to spend the afternoon moaning about what primary school teachers and curricula don't do, because we can't change that quickly. We can only work with what we've got and the learners we've got. And so there's no point pushing it back into primary school, at least for today. It's not an either or, it's a both and, if you have that possibility.
Thank you, Craig, and great question, Sarl. Thank you, appreciate it. I mean,
Chris,
the one thing.
Sorry, Chris.
Yes.
What would be useful to know from teachers, from folk who are online, is to what extent they are able to make use of technology in teaching geometry. And I'm not saying, do you have the skills? I'm saying, do you have the time? Is it actually doable? To what extent is it doable? I'd really like to know that, because I think we preach this tech, but I think on the ground, in the reality of the pressure of classrooms, I really wonder how much time is actually used meaningfully for using technology in teaching and learning geometry.
if you can just pop up your hand, 30% of the educators online say that they have the infrastructure to use the tech in the geometry learning.
Doesn't mean it gets used. And that's not a criticism. It's an understanding the reality. That for me, I'm not wanting to point fingers. I'm wanting to understand the reality of what teachers face every day.
In your opinion, how does construction as a topic in grade 8 and 9 link with the geometry they do? Is it of any significance to do construction before geometry?
It's a really important question. Construction is kind of set up as a part of the curriculum, and I'm not convinced at the moment that it can deliver, given that for the time it's allocated. So much as I have loved doing constructions with pre-service teachers and all the explorations you can do with that, I'm not convinced it's the best use of time. I think folding and cutting and construction, I'm assuming you are meaning here compass and straight edge, right? That's what I'm meaning when I say construction. I don't think that it can deliver to the extent of the time it takes to teach kids how to work with that stuff. And that assumes you're in a context where they have a compass and they have a ruler that's straight enough and all the rest to be able to work with. So I know that there's some people and some colleagues who would disagree with me, but where I sit right now, my recommendation to the national department is take constructions out. Not because I don't think they're important, but I think that time can be used in more productive ways, given everywhere all the stuff is going on in our country, and for many kids, 2 years of lost learning due to COVID. So it's a pragmatic answer, not a mathematical answer. But hopefully it's an honest one.
Thank you so much for your insights. Is there any last thing you'd like to say before we move on to the Neo Series feature focus?
Just a promo for the materials that we've developed. So this stuff is freely downloadable from the website and the URL is there. It's pitched at grade 8 and 9. And you can see in the top corner the topics we've got. We don't even go to congruence. It's that simple, the materials. And certainly we've had really good feedback from people who are looking for stuff for kids who are like nowhere on the page, particularly in grade 9. So we share that, hoping that they are useful for teachers and for learners. All full solutions for everything. Every worksheet has full solutions. So yeah.
Amazing. Thank you so much. I see Carl has dropped the link in the chat. Thank you, Carl. If you can maybe try get that link to hyperlink so that people can follow it easily, because I see it didn't render as a hyperlink. Yeah, and thank you for everything you do in the community, Craig. And thank you for your time. We really appreciate it. To finish off, I'm going to hand over to Lucy to give a brief overview of revisiting the library leaderboard. So Lucy, over to you.
Hi, everybody. It's lovely to meet you. So what I'm going to take you through very briefly is what kind of insights you can get on the Neo Series dashboard as an admin. So you're able to see how your learners are engaging with the content, with lessons, with the units, which is a whole bunch of lessons together, and then assessments. So this is the dashboard on our demo campus. Unfortunately, I can't show you an actual live school campus because of Poppy. I'll be showing you real learner names and real learner details, but we do have some wonderful fake learners on our demo campus where I'm able to show you what work they've completed and what they've done so far. So this is the landing page that you would see when you as an educator and your learners log in, but the difference is as an educator, you have the educator menu item here. We have added some tool tips, which are these nice little icons here, which can help direct you as to what is this thing that I'm looking at. So on the admin dashboard, if you click admin dashboard, this is what loads and what you see as an educator. As you first log in, you see some activity on your campus. You can see over the past 30 days how many lessons and assessments have been completed, numbers of learners that have logged in. So it's a nice overview. But from there, what I'd like to show you today is the library leaderboard. I want to note that we do have a little video that's embedded here in this tip if you need a refresher on what to do with this feature, and the same thing for library progress. If you need a bit of help, we do have the little video embedded there for you so you can see exactly how to use that feature. So the first step is on your library is to choose what library. So many of our schools only have the maths library. On our demo campus, we have all the libraries available. In this instance, I'll choose maths. I'm not going to select a group or date range, but that might be relevant for you. The group might be you want to only look at a specific grade or your specific class, and you'd like to filter by their details. And then the date range gives you the opportunity to see most recent activity. In this instance, I'm going to show activity of all time for the learners, because our demo learners are maybe not as active as some of your real learners. So when you see these 3 dots, it basically means it's pulling a report. So you just have to be a little bit patient and wait for the 3 dots to load. It's basically getting us the most real-time data of all of the lessons and activity. So here on Maths Library, if I log in, I can see these are the top learners for activities on the campus, the most active learners that are on our campus. So I can see this particular learner has done 13. She's actually, many of you know, Tracy has met her. So 13 of our learners, 13 activities completed. That's 8 assessments and 5 lessons. And then as you go down here, the other names here are employees at Advantage Learn. And then we've got some demo accounts that we created. So as you go across, you can then see what is the most popular lesson or the most popular assessment unit. So here I can see the most popular lesson is adding integers. It has been completed 21 times. I'm going to skip over to the unit. So the way we organize our content at Advantage Learn is hierarchical. So many lessons and an assessment fit into a unit, and then several units fit into a path. So this is nice to give you an overview of what topic really has been the most popular on your campus. So we can see there have been 63 completions for this unit on algebra. And then on paths, which is at the higher level, we can see that the most paths that have been completed or engaged with is the Cambridge paths. So let's go to our lesson leaderboard. So I'm going to have a look and see adding integers. I'm going to click that, and that actually opens the library progress view. And then the same thing for the assessment leaderboard. So what is the most popular assessment on our campus? And let's have a look at which one that is. So I like, when I'm looking at data on a specific campus, to see the activity, I always start at leaderboard, and then from there I click into the library progress. So I'm going to choose this one, simplifying complex fractions. It's been completed 10 times. This is the library progress, and I will also show you how to do this from start. So this is one of the most popular lessons that's been completed. I can see here which learners last updated on this lesson and if it's completed or not. If it says that somebody was active on this lesson on the 18th and it says that the lesson's not completed, then that basically means that this learner started the lesson, but they didn't watch enough for it to be marked as completed. I think for our video lessons on our campus, you have to reach about 70% of the watch time, and then it automatically marks you as complete. So here I can see Tracy completed this lesson. Great job, Tracy. Our demo learner number 6 completed this lesson, but Michaela, who's another team member of ours at Advantage Learn, she started this lesson but did not complete it. And then the same for the progress, library progress of an assessment. So this was one of the most popular assessments on our demo campus. And here I can see the different grades that people got. So of these learners here, we've got, it looks like 9 or 8 people completed, and I can see the mark that they got for that assessment. I do want to note, if you have groups obviously larger than 10, click here and you can pull down to up to 100, and then from there you'll move from the pages across. So we have 168 people on our campus here, so I would view them on page 1 and 2. You can also quite easily pull this across into Excel. You simply highlight the data you want, right click, copy, and then paste into Excel, and you've got yourself a report. If that is a useful thing for you, you can search for a specific person's name. So Quanta is another team member of ours, so I can see exactly what Quanta's done on this assessment. So that is how you get from library leaderboard across to the progress. And now I'd like to show you, if you started progress, what does that journey look like? So again, you're going to choose your library, and you can filter by group. And then in this instance, what can be quite helpful is you can go across and see specific paths. So we like to organize our content in paths according to the grades. We find that quite a helpful view and something we think would be helpful for you. So here I can see Tracy again has completed 3 of 339 activities in this entire path. So you can get a view as to how your learners are engaging with, for example, the full grade paths or a unit path. A unit path might be like algebra, a specific topic of algebra. Here's where you would check a specific lesson. So let's look up a lesson on integers, and let's see how our learners are doing on an integer lesson. There we go. Okay, let's choose integrating by parts. Let's see if any of our Advantage Learn staff. So not many people have completed this lesson on our side. This isn't a popular lesson for our demo learners. And then on the assessment progress, again, if you know the name of the assessment that you're looking for. So let's look up simplifying complex fractions. and then we'll see the activity. So that is the summary of the data you can get on those two areas. It can also be helpful to look at a specific learner on the leaderboard if that's what you would like to do, to see a specific learner's activity, but I'll leave that for our next webinar. So thank you so much.
Thank you, Lucy. That is awesome. Great to see. You know, technology is not always that easy to engage with, and it's good to see these things over and over again as we start to use them as we start to adopt them. Thank you so much for joining us. Thank you everyone online for joining us for the Educator Session.